Let's resume. Welcome back. If you were here in the last session, can I get a show of hands, please? Who's new to this section? Who didn't come to part one? You two are fine. You understand this stuff. Okay, so in the previous section, it was mostly me talking about iterators and the audience looking confused because I was talking about iterators and I talked that promised ranges. That was all motivation for how we implement a range adapter. And in this particular section, we're actually going to be implementing a range adapter. But before we continue, I need to let you all know that although I work for a company, this is a personal presentation. Any views, opinions, or statements represented in this presentation are personal and belong solely to the presentation owner, myself, and do not represent those of people, institutions, or organizations that the owner may or may not be associated with in a professional or personal capacity unless explicitly stated. Okay, so as just a brief recap for the people that weren't in the room last time, there are many ranges, sorry, there are many views in C++20. We had string view from C++17. We are getting span in C++20. Those are both in namespace std. In namespace ranges, we get a plethora more, but that is not the complete set of ranges. There are at least 70 in range v3, which is one of the canonical implementations of ranges outside of the standard library. And even that is just a survey of the number of different ranges that we can possibly have. It's similar to the algorithms from the STL. They're only a survey, which is me paraphrasing Sean Parent, paraphrasing Alexander Stepanov. The next thing to explain or to talk about is that we have this concept called a view. We say that a view refines the concept of a range where the range is semi-regular, that is that it is copyable and default constructible, and that there's a Boolean called enable view that allows us to opt into being a view. And then we also have semantic requirements that basically state that we need to have a constant time copy, a constant time move, a constant time assignment operation, and constant time destructibility. Then we talked about slice view, which is essentially taking a few elements from the range, but discounting things that come before the position we want and ignoring things that come after the position we say that reaches the end. These are both examples of different slices. And we talked about how it's possible to implement a slice range adapter closure using a lambda and things that we have in C++20. So it's not exactly an interesting particular range adapter. Then we talked about stride view, which is something that can't be implemented in terms of another range adapter in C++20. So this is an example of a stride view where the stride is size 1, and that means we consider all the elements in the range. Then we have a stride with a stride of size 2, it means we consider every second element, and a stride of size 3 means that we only consider every third element. And so this is where we finished off. And so we're now going to go and look at how to implement stride view in C++20. Now, everything that I'm about to show you has been checked on MSVC's preview 3, and I checked it last night, so everything should be working fine. If you find that there is something that I missed, just please send me an email. That's the fastest way for me to update the slides. So without any further ado, let's move on. So the first thing we do is we define this type called stride view, and we say that it is derived from this other type called view interface. Now, view interface we'll come back to about midway through this presentation, but what it gives us immediately is that enable view. Essentially, view interface has a property in it that turns on enable view. And so that it is unique and we can access all the elements properly, we rely on CRTP to produce stride view as part of its type. Now, what we also require is that our template parameter requires, it needs to model the concept of an input range. Recall that an input range is a range that has an iterator whose type models an input iterator. And then we also require that R models a view. Then what we do is we provide a default constructor because we need a semi-regular type, and we also have a constructor that actually allows us to provide meaningful information. That being, we pass in a range and we pass in a difference type of the iterator to the stride. Now, in the last session, we talked about iter difference t. Range difference t and iter difference t are related. So if we have, if we take the range difference t of a particular range, then it would give us the equivalent type from the iter difference t of the corresponding iterator to the range. It's just a shorthand, so that way our nested types don't spiral out of control. Then we have two helper functions. Basically, we get the base back. The base refers to the base range, whatever we passed in, and we get back the stride. So we're able to get all the necessary information should we actually want to use it. And then, because we have a range, we want to have a begin and an end. We want to provide both the const qualified and the non-const qualified overloads. And then we also have a size function, which gives us back our size in constant time. Now, there is a concept on here. We are requiring that the underlying range, or the base range, models a sized range. Now, we talked about in the previous session the concept of a size sentinel for an iterator. And these two concepts are not related. A sized range is something that basically says, can we call range's size on this range and get back the number of elements in the range in constant time? So an example of something that models a sized range is a vector. Another one is a list. But unlike vector, lists iterator does not model a size sentinel for its iterator because we do not have, we're not able to get the number of elements between two iterators in constant time. Are there any questions on that? I see none. Okay, so the detail section is that we have a type called D, which we're going to use as a shorthand for the range difference of the range, and then we store the range, we make sure everything is default constructed, and we store the stride as well. We'll also have a type called an iterator. This is really why the whole previous section was important. And it's templated to reduce the amount of code we have to write. So we have to write one iterator with a bit of extra complexity, but significantly less code duplication that is pretty much copy-paste. And then we also have a static function called end implementation. This will become very important toward the end of this session, about 3/4 of the way through. And finally, we have an algorithm called compute distance that will tell us the number of elements that are actually in the range. Finally, we need to provide a deduction guide, and a deduction guide allows us to not have to specify what the type parameters are. We can just call stride view with a range and a distance. And what we say is that the type of the stride view is for any given range, or say any given reference to a range, we have this thing called all view, which allows us to adapt a range that doesn't model a view into a view. And that's what the viewable range concept is also requiring. Can we take a range that may or may not be a view and adapt it into a view? And for those who are new to the session, so a range adapter is something that it takes a viewable range as its input and gives us back a view that may have altering properties. That way we can produce some sort of transformative operation. Okay, so let's move on to the constructor. It's very straightforward. We're just simply constructing the elements and putting the things we get from the constructor into our elements. Our base and our stride are fairly straightforward. We're simply returning the members. And here we come to the getting the iterator and the sentinel. So with begin, it's fairly straightforward. We have for the non-const qualified overload, we have a false, and for the const qualified one, we pass in true. For end, we're just going to defer to end impl, and although it seems a bit redundant at this point, we're going to simply call ranges end on the base. What we'll do is we'll come back to this a little bit later on, and we will refine it so that way it makes a bit more sense. But for now, it's really just something that's a bit boilerplatery. I see a question. Could I give an example of a range that is not viewable? A temporary container. Thank you, Eric. Thank you, I blanked on that. Yes, so temporaries are not viewable for lifetime reasons, I believe. I see a nod there. Okay, so here we have the size, and we're going to call ranges size because we have a sized range. What's the problem with this? I mean, beside the fact that I've got obviously lots of white space there that's alluding to something else being added, what might be the problem of just calling ranges size on a base? It doesn't take into account the fact that the stride will make it skip elements. That is absolutely correct. And so what we do is we pass the size actually into compute distance, and we define compute distance as such. Essentially, what we do is we take we divide it by the number of elements that we divide the number of elements that we have in the full range by the stride, and then there may be a few left over because there may be some extra elements, and in that case, then what's going to happen is we need to consider that case and add that to however many elements we're going to be stepping over. Now, the reason it's requiring an integral instead of just taking the range difference is because range size, its type may or may not be signed, and so we need to account for that, but we're also going to be passing in a type that is potentially signed. So this is an easier way to describe this instead of having two overloads. And now we move on to defining the iterator. So the first thing we do is we provide the structure for it, and what we're going to do is we're going to define a few types. So when we're talking about the parent, we're actually referring to a possibly const qualified version of the stride view. Maybe const, what it does is it takes a parameter, so it takes a boolean to indicate is the iterator const, and if it is, then it const qualifies stride view. Otherwise, we're just referring to a mutable stride view. The base is a possibly const qualified version of R, and we're going to say that the inverse constness of the iterator is a friend of our iterator type that we're actually working in. We also want to have a pointer to the parent, and that will allow us to actually get the stride and work with things a little bit more easily. We're going to have an iterator to the current element that we're actually at, and then we're going to store this thing called step. We'll come back to step much later on. It's not important right now. Then we have a member function called advance. This will allow us to actually take arbitrary steps. And finally, we have a helper function called compute distance because friendship is not transitive, and so just because the friend operations are friends to the iterator, that doesn't mean they're friends to the parent, so we need to define this locally. And so when you see compute distance, it's really just deferring to the parent's compute distance. Next up, we need to define the difference type and the value type. These are just we just get these from the base of the range, and then we also add this thing called iterator category, and it's a bit involved. So I'm going to take a moment here. The first thing we need to do is make sure that we are not saying we have a contiguous iterator, because having a stride is the exact opposite of being contiguous. The elements are sparse instead of compact together. So So what we say is that if it models random access, if our range models random access range, then we're going to say that it's just a random access iterator. Otherwise, what we're going to do is we're going to defer to this other type that looks at what's inside the iterator traits of our underlying range's iterator type and get the iterator tag from that. So if it's a bidirectional iterator, then we'll get that tag, and if it's a forward iterator, we'll get that tag, and so on. Ben? So Ben asked, am I saying that if random access range would normally give us a contiguous iterator tag? It won't do that. I think I misspoke. What I meant was that a contiguous iterator models the random access iterator requirements because it's a refinement. And so if we meet the requirements of a random access iterator, we can bail there and just say it's a random access iterator because we've already met all the requirements that are necessary. But if we consider that it was a contiguous iterator, then we're just doing a little bit of extra work, and then we're going to say it's a random access iterator anyway. Does that answer the question? Okay. Are there any other questions? I see none. All right. So now let's define some of the public member functions. And so what we're going to do here is we, again, need to model the semi-regular concept. So we have a default constructor. That's fairly uninteresting. We have an explicit constructor that gets the details of the parent and puts them into the iterator. What we have here is we take the address of the parent, and then we call begin on the parent base, and we store that. David? So the question is there a reason to use a pointer instead of a reference to the parent? And I believe that is for standard layout reasons, but I could be wrong. Copyability, thank you. Yes, that makes more sense. Copyability and assignment, yes, thank you. So does that answer the question? Cool. So the next thing to look at is the non-const, that weird constructor that I talked about earlier. So what we, sorry, I didn't talk about it earlier, I talked about the friend earlier. What we're going to do here is we're going to say that the const iterator, or the const qualified iterator, is allowed to construct an iterator from the non-const version of the iterator. And so what we say here is that we have a dependent context, and we're going to construct an iterator based on that when only when isConst is true, and we can convert an iterator from the underlying range type to the possibly const qualified range type. And then we're just going to steal the data otherwise. It's not a copy constructor, but it does look like a copy constructor. Margaret. So the question is, why is there a template head there that says bool const2 equals isConst? Is that correct? So the reason for that is because we need to force this to be a dependent context. Otherwise, the compiler is basically going to say, well, this is a copy constructor in the non-const case, and that because it's got all this extra stuff on it, it just doesn't work. So that's essentially why it's there. It's something you would experience in template meta programming a lot. It's unfortunate that it still needs to be there. Does that answer the question? Cool. Okay, so next up we have the base operation, which just gets us the base iterator, which is the current one. And then we have the input iterator operations. So for this, we need to have the source or the dereference operation, and we have the successor. We just defer that to advance, which will be on the next slide. And then you'll notice that the postfix iterator, increment operation, has a return type of void. Now, if you have written an iterator before, then you will potentially be surprised by this. The definition of an input iterator requires that it's weakly incrementable, and what that means is that it has to have a prefix increment operation that returns a reference to the same iterator, but the postfix just needs to exist. It doesn't actually have any mandated return type. We'll come back to the postfix one in just a few minutes. First off, we'll look at the advance operation, and that takes a difference type. And so what we do is we call advance and we multiply the number of steps we want to take by the stride. And so what that will do is it will increment current, but if we have something that models a random access iterator, it can do that in constant time, so we don't have to have a loop that just iterates over that. It's an algorithm helper. And the reason we have the ranges end at as the last parameter, what that means is that once we reach the end, we're not going to try and go any further. It's a case of we've terminated, let's just stop here. And this works for forward ranges and input ranges, but it doesn't work for bidirectional ranges because we can also go backwards with bidirectional ranges. So what we need to do is we need to provide a way of moving backwards. And so what we do is we check that if we're a bidirectional range, and then we also check that the direction we want to move is backwards, we move in the opposite direction. So our sentinel is now going to be the first element to the range, and we stop there. Are there any questions about that? I see none. Okay, so then we have to care about the comparison operations, and so we check that current is equal to other, and then we also have an operator for checking not just against a sentinel, but also against an iterator when the iterator is equality comparable with itself. Now, if you have a forward iterator, you get this for free. But in the event that you don't have a forward iterator, what this means is that you have you have to make sure that the iterator has both equal to and not equal to implemented, and the operation is reflexive, symmetric, and transitive. And thanks to the spaceship operator in C++20, we don't have to specify anything else for equality. We don't have to specify the not equal to operations because those are the compiler does some extra steps to make sure that we get that when we say x is not equal to y. And in the case of the sentinel, we don't have to provide the friend that would say we have a sentinel and an iterator because the spaceship operator also takes care of that. Jonathan Muller is giving a talk later today about the spaceship operator, so if you're curious about that, I highly recommend you go and watch that. Then we move on to the forward range version of iterator. The increment. And the a forward iterator requires that we model a concept called incrementable. And this incrementable refines what weakly incrementable does, and it means that the postfix increment operation needs to return an object of type iterator. And so that's what we're doing here. We're taking a copy, and we are going to increment the current one, and then we return the copy. And what we do is we put on a requires clause saying that we require this operation exists if and only if we have a base modeling forward range. So it's not there when we have an input range. The compiler won't consider it. And then in the event that we do have a forward range, only this one will be considered. Are there any questions about that? Okay, I see none. The next thing to do is to consider the bidirectional range case, and that is for moving backwards. And so we say that if we have a bidirectional range, and then we can move in the opposite direction. We don't need to have a void returning a decrement operator for postfix because anything that models a bidirectional range is already a forward range, and so we already have something that is incrementable, and it means that we can move backwards as well because we model bidirectional range. Then what we need to do is we need to implement the operations for random access iterators, which are plus equals. We need to be able to do that in constant time. We have the arbitrary plus operations notice that unlike the spaceship operator additions for consistent comparison, we need to provide both ways of doing this. We then also have stepping backwards by an arbitrary amount in constant time, and then we also are able to compute the distance between an iterator and its difference type, and between the distance between two iterators. That allows us to work this out in constant time. Then we have the subscript operator, which is really just referring to things that we previously implemented. And following on from that, we have the comparison operations, and they're very boilerplatery, but they all require random access range. And in the case of the last one, which is the spaceship operator, we also require that the iterator to the base is going to be what's known as three-way comparable. And three-way comparable makes sure that we can use all of the above operations as well as the spaceship operator. And the reason we have to support all of this is because older iterators may not have when we first start using things such as this, they won't have the spaceship operator, so we can't take advantage of it. We need to provide a way of hooking into that, and it's done like so. Are there any questions about that? I see a question at the front. Adi. The question is, why are the comparators there if the spaceship is provided? And my understanding is they're necessary because older iterators may not have a spaceship, and that will cause problems for those particular iterators. Does that answer the question?
The spaceship is defined only conditionally.
That's correct. So the response from the audience was that the spaceship is only there conditionally, so we need to support all of the rest, and that's also important to note as well. Does that answer the question, Adi? Okay, Divi? Couldn't you implement the spaceship? So the question was, couldn't you implement the spaceship operator in terms of the other operations if it doesn't already support the spaceship? And I don't really have a good answer to that. Can I have a bit of time to think about that, take it offline? Thank you. That should say auto. Thank you for pointing that out. So the point was that the spaceship operator returns a bool. It should actually return auto and return whatever the spaceship operator actually is supposed to return. Then we have, before we move on, are there any other questions about this particular slide? I see none. Okay. Following on from this, we have two helper functions. One's called EtoMove. EtoMove is an operation that essentially allows us to do, in one step, StdMove of dereferencing the iterator. It's a bit more involved than that, but that's the platonic description that I can fit in a sentence. And iterswap is, like EtoMove, a helper function that allows us to swap two dereferenced iterators. We're simply going to be deferring these to the range-based, to the range implementations, and they will resolve everything with respect to the current respective current iterators. All right, it's time for a test. Let's write a test, and in this case we have an iota view, and we're going to stride over that every 10th element. And so what we're going to do is we're going to assert that we have a random access range and that we also model a view. And so both of those pass, and we check that the elements are equal. So the thing we get back from stride matches that we are actually stepping over every 10th element. Sorry, considering only every 10th element. So this works, and it's all working fine. We're done. We can go now. I hope you enjoy the rest of the conference. But problems start to arise. So here we have a filter view. And filter view allows us to remove elements from our range that don't satisfy a predicate. This also works, actually. And so that's great. There is a slight problem with this, and that is when we const qualify it. Because not all ranges can be const qualified. And that is because something such as FilterView allows us to, it is required to cache an iterator, so that way its begin happens in constant time, because begin and end are required to compute their iterator and sentinel in amortized constant time. What happens is the first time you call begin, it will perform a find if not, one of the two, and then that's a linear operation. If we do it once and then return a cached iterator, that's going to be okay. But unfortunately, we can't even say that we don't have something modeling a range, because at the moment we have a const qualified overload of begin and end, and so the compiler is going to pick those up and try and use them. But then when it goes to the underlying implementation of begin and end for the filter view, what's going to happen is it's going to run into problems there and say that it doesn't exist. And the output that I've seen getting back from that is not very pretty. So we want to fix that. So I just want to take a step back and reiterate that not all range adapters can be const qualified. So that's something that's very important. Filter and I believe drop while are two examples of things that can't be const qualified. Are there any questions at this point? I see a question over there. Would you mind coming to the microphone, please?
The issue you described with the filter view,
yep,
the odd or even, sounds like an internal implementation detail, in the sense that mutable should be used there, so that begin and end could be const. Couldn't that be a solution?
Sorry, can you please repeat that?
So, as far as I understood, the problem with filter view on is odd or is even is that the begin and end have to modify the view for the first time.
That's correct.
That sounds like an internal implementation detail that shouldn't leak outside. So rather, the implementation should use mutable inside and have the begin and end const.
I thought so too at first. I can see Eric leaning forward at the moment, so please do pounce if I get this wrong. But my understanding for why this can't, why we can't use mutable is because of a particular rule in the, I think it's the concurrency section of the standard library that basically states that we need to make sure that we don't have any data races. And I can't remember the exact wording, but I can remember the stable name, which is how you look it up, because I've had that quoted at me several times. It's called res.on.data.races. That's res.on.data.races. And it essentially means that we can't use mutable because that could lead to having a data race which is undefined.
Okay. In this case, I think it wouldn't. It will essentially do the same operation many times, but it wouldn't be a race. But I understand the problem. Okay.
Did I miss anything there, Eric?
No, that's right. And the issue is that you can have the same const filter object access simultaneously from different threads.
So the
Two different threads are trying to call begin the very first time. They're going to try to have a concurrent access, concurrent write to the same data member in that object. Basically, res on iterators means that const has to be const.
So the takeaway from that, I'm going to very much paraphrase what Eric just said there. Thank you, Eric. But basically what Eric just said was that res on data races means that const must mean const, and we could have two threads calling into begin, and that would potentially lead to a data race. Could you do it in the constructor instead? I actually don't know the answer to that, but that may have problems with the requirements of a view. Yep. So it means that we don't have a constant time operation anymore.
But wouldn't the as-if rule apply here? Because even if you have not 2 but 10 threads doing the same thing at the same time, but they would all be writing the same value. It's not that one would calculate one value and the other different value, so then you would have a race. In this case, you'd only have 5 threads computing the same trivial thing at the same time and then writing it 5 times more than necessary.
So the response was that, did you say functional databases? Functional code bases don't work like that. Okay, thank you. Okay, so let's fix this. So for the record, FilterView does not even have a const qualified begin and end. It just doesn't exist. So let's fix this for StradView. And so what we do is we require that our range for the const qualified begin and end model a const qualified. Sorry, the const qualified version of R of the base range models a range, and the overloads only exist in that case. Otherwise, the implementations are identical to what we saw when we first looked at them. In the case of size, we have a const qualified size range. We don't need to say, we can just stick that in there because sized range is already modeling a range. It's just a refinement, so we can simplify it a little bit. And we also can eliminate a certain number of overloads for begin and end in the event when we have a range that can be const qualified and its iterator and its sentinel are the same type. We can figure out the non-const qualified overloads because they're basically, to my understanding, going to produce the same result. And so what we call this a SimpleView. Now this is an implementation detail, this concept, so it's not a vocabulary concept, but it does exist for people who are going to build their range adapters. And you only have to implement this once, and if you were building something on top of an existing ranges library, then you'll probably find that it already exists. And then what we can say is that our non-const qualified versions have a requirement of not modeling a SimpleView for the non-const qualified version of R. Are there any questions about that? Okay, so I see none. The reason for adding this particular requirement on is to reduce the number of instantiations of member functions. And so now, when we do this, we're still not going to be able to have a const qualified StradView of a FilterView of an IotaView, but we can at least say that we can't get that. So this test will now actually compile and pass instead of being problematic and giving us an instantiation error. Now let's talk about element access. Element access is something that a vector can do. So we fill up a vector with some random integers. If we want to access an arbitrary element, we can use the subscript operator. And if we want to access the first element, we can say that we want to access the front of the vector. And if we want to access the last element, we can say we want to get the back. And if our underlying range has these operations, it would be nice if our StradView also respected these operations and behaved in the same fashion. So we could do something like this. Now, you may recall at the very start, I talked about this thing called view interface, and we derived our StradView from that. And view interface provides us with a large number of operations that we just get for free if we inherit from it. For example, there's a size operation that works when we have a size sentinel, but we still need to provide a size range version of the overload. In the ones that I want to focus on, in particular, are front, back, and the subscript operator. Now, it turns out that we already meet all the requirements for front and for for the subscript operator, because in the case that we have a forward range, we model, we've just met all the requirements, so that one exists when we have a forward range. In the event that we want to do a subscript operation, we have a, if we have a random access range, everything just exists. But unfortunately, this doesn't work for the back operation. We need a bidirectional range. We already meet this requirement if we have a bidirectional range. But the thing we haven't accounted for is that we need a common range as well. Can I get a show of hands, please, for those who didn't come to the last session, or those who want a refresher on what a common range is, please? Okay, so a common range is a range whose whose begin and end are the same type. So that means that the iterator and the sentinel are the same type. And so we don't meet that requirement yet, and we should probably fix that. So let's get StradView to model common range. You may recall that we, much earlier on, talked about endimple, and that just returned basically what you would expect our .end to do. But in the event that we don't model, so in the event that we have a range that is both sized, that is we can call ranges size on it, and we have a common range where the iterator and the sentinel for the range are the same type, we can make it a common range. And so what we do is return an iterator to our StradView instead. So what we do is we check the constness of self, which is the templated version of the StradView, and then we pass in the iterator, so the range, and we also take the number of steps between the last element we want to consider and the end, because that's all the information we need to get the back. Are there any questions about that? I see none. Okay. Then moving on, we haven't provided that constructor yet, so we need to do that. And this is what it looks like. It's very much similar to the rest of them. The only difference, aside from the requirement and adding a step parameter, is that we are also setting current to the end of the range instead of the beginning of the range. And now this means that we can call .back on our range as well. Are there any questions about making this a common range? Okay, I see none. All right, let's take a look at this particular test case now. What we're saying here is that we have an iota view, and we're going to stride. So there's 100 elements. We want to take every 33rd element. So that means and then we want to reverse it. And so this means we're going to lazily reverse the number of elements in, so we're going to lazily iterate essentially backwards in a strided fashion. Can I get a show of hands, please? Who would expect this to be if we're going to take the stride forward, which would be 0, 33, 66, 99? Can I get a show of hands, please? Who would expect this range adapter to, in reverse, produce 99, 66, 33, 0? Okay, I see a few hands. Who would expect it to not do that? Eric, get your hand up because of future slides. What we expect, like as in what we functionally expect this to behave as, not what we expect the code to do. Because anyone who is skeptical of this is absolutely right. We actually get 67, 34, and 1. And the reason for that is because our back iterator, our stepping backwards doesn't actually account for there being a precise number of elements in the strides. And so we need to do that. So you may recall that I kind of really superficially glossed over this thing called step. And that's essentially what's going to be the star of this section. So we're going to revisit advance. And you may recall this bit here from the previous section. This is now going to be wrapped inside something that is not a bidirectional range. And then what we're going to do is we're going to do some computation. The first thing that we want to do is we want to compute the number of steps we take whenever we iterate forward. And so the way ranges advance, the way the bounded version of ranges advance works is that it returns the difference between the number of steps we expected to take and the number of steps we actually took. So if we expected to take 10 steps and we only took 5, ranges advanced will return 5 to indicate we didn't take 5 steps. And what we're going to do is we're going to subtract that from the actual stride to indicate this is where our step is. And so this is how many, this is actually how many things we need to move backwards in the event we want to move backwards if we're at the end, because that's where the stride actually stops. And in the case of when n is less than 0, our stride is it's a bit funky, but what we do is we say that if the step is 0, then we take back, we step back the number of steps that are equivalent to the number of steps we want to take times the stride. It all works as before. But in the event that we want to move from the very end of the range, what we need to do is we need to say that we're going to move back a certain extra number of steps to ensure that we account for however many elements we skipped over, but we didn't actually reach another thing in our stride. And then what we do is we move backward and store a value in stride. Are there any questions about that? I see none. Okay, and this means that our reverse will actually work now. Now, part of the great thing about ranges and range adapters is that they compose really well. And this particular example with the pipe operation works. It just magically works out of the box because views reverse is something that has already been accounted for in the standard library or in the canonical implementations, and so we can move forward by piping stride view into reverse. Unfortunately, this fails because we can't pipe iota into stride because it doesn't actually understand what a pipe operation is. And so this final section is going to be focusing on how to get that to happen. What is the machinery behind the pipe operation? And so I'm going to take this as slowly as I can, but if you have questions, please do interrupt me. So the first thing we need to talk about is what a range adapter closure is. So on screen, we have a range adapter, that's stride view, and we have view stride. And view stride is a range adapter closure object. And what this means is that we can say view stride of ints and 5, and that will give us back a stride view of an iota view where we have a stride of size 5. And that is equivalent to piping ints into views of a view stride of 5. So these two expressions should be equivalent. If we do one, it must be the same as doing the other. And so what we have here is our closure. What we call this is, this is how we describe what stride function, this is how we describe the view's stride as a type. What we say is that we have a call operator, and if we pass in a range and a step, then we can construct a stride view. We wrap it inside this thing called views all, so that way if we pass in a non-view, but it's a viewable range, it's suddenly a view. And this gets us the left-hand side of the expression, the stride with the ints and the 5. But what we really want to have is also the other side, where we can pipe ints into stride of 5. And so the way we do that is we return an operator, a call operator, where we take an integral and we have this thing called a range adapter closure. And this is where all of the fun stuff happens. So we're now going to build the range adapter closure. And the range adapter closure is derived from a tuple. There are better implementations if you're actually doing library development, but for the purposes of this session, we're just going to say that it's derived from a tuple. And we want it to be semi-regular, again, because that's part of how ranges are designed. And we're going to have a constructor that takes both the object that we want to be calling, that's f, and the arguments that we don't want to consider when we're actually calling when we're actually calling our range adapter. And so both of these things need to be copyable. So semi-regular refines copyable, and it also Anyway, so what we need to also do is have a call operator that works with a viewable range, and we need to say that it is invocable with respect that f is invocable with respect to a range that we're passing in as our parameter, and all of the arguments that we have as our parameters that are already being cached. And this is there's a const qualified one and a non-const qualified one, and we're not going to consider the const qualified one just for the sake of simplicity and time because they're identical. And then what we're going to also have is this static member function called apply. Can I get a show of hands, please? Who here is familiar with std_apply for tuples? Okay, that's wonderful. I will explain that in just a moment. It is very similar to that. So the first thing to do is to make a constructor. I didn't have it on the previous slide, but this base T refers to the tuple of remove references of the arguments, and so we're just going to make a tuple and forward everything into said tuple. Then we're going to make a call operator, so it's as it was before, and we're just going to forward everything to the apply. Now, the reason that what apply does is it forwards on the elements of a tuple into a call operation. And the reason we can't just use std_apply is because std_apply, to my knowledge, only allows us to have one tuple passed in as the arguments to a function, but we need an extra parameter, which is the range. And so we need to build our own apply. And this is the only section where we really do any template metaprogramming, because we are relying on std index sequence, which allows us to produce a sequence of integers between 0 and the number of the number of arguments that are going to be at the back of the call. And what we do is we default construct our callable f. That's why it needed to be semi-regular, because we wanted to default construct it here. We didn't actually want to store anything because there's no real need to. And we just forward on all the arguments. Finally, what we need to be able to do is pipe. And we haven't done that yet. But if we declare a friend function that is the pipe operator, and we pass in a range adapter closure as the right-hand side and a range as the left-hand side, sorry, a viewable range as the left-hand side, and the range adapter closure is invocable from the range, then we can call that and return the result that we would get back from that. And you'll notice that I've provided the R-value reference one. I'm leaving it as an exercise to you all to implement the remainder. I'll give you a hint, they are very similar to implement. And finally, the final thing about the range adapter closure is we need to provide a deduction guide. And the reason for that is because we don't want to preserve any reference information in the type of the range adapter closure. And although we have a remove reference in the base type, the tuple, we still need to remove that before we even get there. And so that's how we do it here. Finally, the finishing touches, we want to provide an object that is our range adapter stride. And this is pertaining to what you were talking about, asking about in the previous session. This is what goes into namespace views. And so that's what we have as our range adapter closure. It's used as such. So what we can do is we can take an iota view, then we can transform it so that way we get the result of the collapse conjecture, and only consider every fifth element. And then what we're going to do is we're going to reduce that, and because it's a common range, it satisfies everything that we have as a reduction, that reduce requires, because reduce doesn't have a sentinel-based overload. And we check that the result is correct. And that is our range adapter for stride. So in conclusion, we built a non-standard range adapter. We built a range adapter closure type. We learned that not all ranges are const qualifiable, and we leveraged the spaceship operator to make things a little bit easier. Furthermore, from the previous session, which kind of blended with this session a bit more than I was anticipating, we learnt that iterators are fundamental to developing a basis for ranges, as are sentinels. They go hand in hand with ranges, and although we don't need to use them as much in our user-based code, they're absolutely important and essential for building range-based abstractions. I'd like to thank you for your time, especially if you stayed here for the full 2-hour session. And I'd like to wish you well for the rest of the conference, and thank you. So I think I have 4 minutes left for questions. Okay, there are none left. Thank you.